Welcome to this video. Today we are going to discuss the topic of potential energy and conservative forces. So what is potential energy? Potential energy is something which is stored in a system by virtue of its position or its configuration. Now what do we mean by terms position or configuration? Position, we can say, let's say I have a heavy block which I am have to carry from the ground floor of the building to some third floor or fourth floor. Then that position of the body is changing and I am expending some work in changing the position of the body. So I am expending the work, and that work is being converted into the form of potential energy of the system, or is stored in the form of some energy in the system. In the same way, I can take an example of a click pen. Now when I click a pen, the spring of the pen gets compressed and my work is getting stored in the form of spring energy of the pen, so it can rebound and convert that energy in some other form. So again, this is a form of stored energy by virtue of its configuration. So this is the definition of potential energy, and how we define gravitational potential energy, which is the topic which we want to learn. So the first form of energy would be gravitational potential energy. So how do we define gravitational potential energy? You might be knowing it exhibits some kind of formula, that is mgh. So from this formula you may be learning that whenever we are changing the height of the block, then its potential energy is changing. For example, I have a block of mass m which is lying on Earth's surface, and I am increasing its height. So when I am increasing its height, its potential energy would increase in proportionality to its height. No matter how I reach from the bottom point to the upper point by a matter of lift or by a matter of stairs, it does not matter what path I am taking. The potential energy of that block would be same in both the cases. So this is what is the idea of gravitational potential energy. So how do we define it? So to define, we write a formula, that is change in gravitational potential energy of a system is equal to negative of work done by gravitational forces in changing the system. So let us use this formula. So if I were to define, symbolize U as the expression for potential energy, U is the system, is the gravitational potential energy. In short, it is written as PE. So at some height, I would say the potential energy of the particle is some U. So the change in gravitational potential energy would be delta U. So I am saying that the change in gravitational potential energy, that is delta U, that is equal to the negative of work done by gravity in bringing about that change. So let us take an example to find the expression for this formula. So we have a mass m, and this mass m is raised through some height, say h. So we can easily say, since action to gravity is g, what is the force acting on this mass? Force acting on this mass is mg. What is the displacement of this mass? Displacement of this mass is h, and since displacement and gravity are opposite to each other, we will put a negative sign, signifying negative work. So from this equation, I can directly say the change in potential energy of the system over here is simply mgh. So this is how we define the change in gravitational potential energy, and by which we define gravitational potential energy. Okay. Now, one thing which I can note in this formula is that change in gravitational potential energy is mgh, right? So, if I were to define, if I were to divide the change in potential energy by the distance traveled, let's say delta u by h, and I multiply a negative sign, so I would get the gravitational force acting on the particle in vector form or in sign form. It also is giving me a negative sign, which shows that the gravitational force is acting in downward direction. So this is a useful way to find the potential energy, the force acting on the system, which is acting on the system. So this is the force acting on the system, that is the force of gravity. So I can write the expression of force as some minus delta u by h. So I can generalize this expression. The force acting on the system, which is the force in this case gravitational force, is equal to, let's say for a small change delta, I can write it as some du, right? And some small change in height, I can write it as some dh or some dy. So this is the gravitational force. Acting on a system. So this is one expression which we can use to identify what is the gravitational force associated with a potential energy, or force associated with a potential energy, be it of any form. Okay. So we have defined change in potential energy and we have defined the gravitational force. But what actually gravitational potential energy means, or potential energy means in gravitational context? How would we ask, how are you able to say that potential energy is always, the change in potential energy is always mgh? Does it depend upon path? These are the questions which usually come in our mind. That if I were to take a different path, would the potential energy, the expression of potential energy change? Or when we are taking the straight line path, would the expression for potential energy change? So the answer is very is a very remarkable answer, that the change in potential energy always remains the same between initial and final points. So this is a very important characteristic of gravitational forces, that the change of potential energy or the work done by gravity between initial and final point does not depend upon path. Let us take an example to feel how this is happening. So let us take a staircase example which I was mentioning in the starting of the lecture, that we have a staircase and there is a person who is carrying some mass. He is currently at the bottom of the staircase and he can take mass to the top of the staircase, which is at a height h, in two ways. He has to take two different paths so that we can verify the idea that potential change in potential energy is always mgh. So this is a very easy way to find. We can directly take this mass and along the stairs. Let's say this path is some alpha. So work done along path alpha, what would that be? We would say the gravitational force acting on it, that is mg, the displacement of the path, that is y, and the angle between displacement and gravitational force. So the angle between displacement and gravitational force is this obtuse angle. Let's say this obtuse angle is some this value is some beta, so this obtuse angle would be some cos beta plus 90 degree. So this would come out to be minus mg y sine beta. This would be work done along alpha path. Similarly, let us take the path, let us take this gamma path. This is the gamma path. So in gamma path we are going to go over here and we are going to take a lift from initial point to final point. So what would be the work done in that case? So I hope that is clear how negative sign came, since cos of some angle plus 90 degree gives a negative sign angle. So work done by in beta case, what would that be? So we are saying that the mass m is traveling along the horizontal and the force acting, gravitational force acting on it is vertical. So that means that the work done by gravity in that particular path is 0, and all the work done by gravity is when it is being lifted up. So that is minus mgh, and we can clearly see work done by alpha is equal to minus mg by sin beta, where y sin beta is h. So this also becomes equal to mgh only. So work done in alpha path and work done in beta path is same. And not only this, we can easily prove that even if we are not going in a straight line path or taking different paths, the work done is always going to be same. So these kind of forces where work done by gravity or the change in potential energy associated with that force is independent of path, these are a characteristic of conservative forces, which is our next idea. So I hope this idea is clear, that work done by gravitational potential energy is independent of the path. Other forms of potential energy, like we can also study here what is spring potential energy, which is also called elastic potential energy. So elastic potential energy we can also study here, but it only has an expression which is similar to what we have already learned. So we will be taking that particular topic ahead, and let us see some questions on the basis of potential energy. So let us take a question. So I have a vertical frame of wire. So in this frame of wire I have a mass m which is situated over here. So this frame of wire has some radius r. Now I have to find what is the gravitational potential energy of this mass m as a function of the angle which this mass makes with the vertical. So this should be pretty easy to find, right? I have to first fix where is my reference, and by reference I mean I can only define the change in gravitational potential energy. So I would be writing gravitational potential energy. This is the only thing which we can define, right? We wrote delta U is equal to minus mg. So how would we write the expression of potential energy that we are learning from this particular question? How would we write potential energy, exact value actually in some case? So change in potential energy, what would the change in potential energy be? It would be some final potential energy minus some initial potential energy. So the final potential energy, I am saying it is at some angle theta, right? And its initial potential energy, let us say we are taking when the mass was at ground. So this is the point which we usually assume, or we take arbitrarily. By arbitrarily we mean we can take any value of potential energy of the mass m, that is the bead which can slide on this frame, by our conscience. That means we can take the value of this mass m, potential energy of this mass m, we can take any particular value, be it 0 or some constant c. So this value is open to us. So we can take the potential energy value of potential energy at this point as 0 itself, because it's a convenient value. So usually it is assumed as 0, but it is totally fine to take the value of potential energy at some constant c also. So initially we have taken the potential energy of the bead as 0, So potential energy at angle theta, we know that change in potential energy in bringing the mass m up till this point would be simply proportional to this height, which would be r cos theta. So we would be writing mgr cos theta is the potential energy of this bead as a function of angle theta. So this is a one question which we want to do, and we have learned a lot from this question actually. The question may be simple, we wrote the expression in a very easy way, right? But we learned something. So what we learned? We learned that first we can write potential energy of the expression directly, which I have been reiterating in my point, that potential energy is the kind of force where the work done by the force does not depend upon the path. So we directly wrote the change in potential energy without going in details how the mass m is going to go there, right? We directly wrote the height and r cos theta and multiplied with mg. So mgh, we formula the formula which we used, mgh, the mgr cos theta is the direct expression. And the second thing we learned is that there is no absolute value of potential energy. That means that everything is relative in terms of potential energy. We cannot say that potential energy has some value this at this particular point without saying that where we have assumed the reference to be or the zero to be. So that's the one thing which we have also learned. Okay. Next we are going to learn about conservative forces. So conservative forces is a topic which is associated with the potential energy. And NCERT talks about conservative forces a little bit, but we are going to go a bit in detail on it because it is very important for competitive perspective. So from our conversation, can you identify an example for conservative force? What would be conservative force? So you might be guessing, right? Yeah, okay, gravitational force is the conservative force. So what is the characteristic of conservative force? Conservative, by characteristic we mean when there is a situation and some particular things are happening or some particular phases are happening. So when those actions happen or those things are likely to happen, then we say, okay, this is the question domain of conservative forces. So the one point where conservative forces are usually found is when work done by a force is only depending on the initial and final points of motion and is independent of the path taken between initial and final point. So I'll write this point. Work done by such a force is independent or is only depending on the initial and the final points of motion. Next, we are going to define this in a different manner, that is the work done by such a force in a closed loop is zero. So these both expressions are equivalent expressions which lead to the same result of conservative force. So in conservative force, what we need to learn? We need to learn one formula which we already saw a hint of. That is, a conservative force can be written as the differentiation of potential energy with respect to the position expression. So minus du by dr gives the expression for conservative force. For example, for gravitational force, it is one way. For electrostatic force, if we know the expression for potential energy of electrostatic force, we can find the force on it. So what are other ways? Let's say if I had an expression of conservative force and I want to identify a conservative force. So how to identify it? So to identify a conservative force or conservative forces follow one more rule, that partial differentiation of the force x expression with y, that is differentiation the fx expression with respect to y. Let's say force is some fx plus fy, then partial differentiation of fx with y is equal to partial differentiation of the y component of the force with respect to x. This is true for two-dimensional forces which we are normally dealing with. And next we can write conservative forces, the curl of conservative force is 0, but for us this expression is more than enough, and this is only what is required. Next we want to do some questions on this expression. So question we will do, let us do jump to the spring forces questions. So there are a lot of questions on which to do on the spring forces. So one of the questions which we can take up, which we did, was that spring was connected to a block and it was on some kind of incline and we had some friction on that incline. So next we are going to take the same case of spring and a block, and this time friction is on the surface. And we are approaching these questions by the work perspective. That means we are concerned with the work done by various forces. So the question is, we have a spring or spring constant K, some forces are acting on it, and some coefficient of friction is mu. So we have to find work done by force F in stretching the spring by some x distance. So that is the work done by F. So that is pretty easily, right? Fx. That's it. We have to next we have to write work done by spring. So what is the work done by spring in elongating the block from this point to this point? So work done by spring, we also know the expression minus half kx squared. Next we have to write what is the work done by friction. What is the work done by friction acting on the block and taking the block from this point to this point in displacing the block through x distance. So that work done would be also simply minus mu ng x. The friction force acting on the block is in this direction, and opposite to that displacement is happening. What is the amount of frictional force? Mu ng, mass is the m is the mass of the block, and x is the displacement, and so on. Now we already did this question, like just by verbally speaking this question, we have already done it. So I have added one more part on this question, which is what would be the maximum displacement of the block from its initial point. So in its first stretch of motion, when the force F was acting on the block, F is a constant force. So when I am applying a force F, up till what distance, maximum distance, can the block F go from its zero elongation position? So we know that work done by all forces is equal to change in kinetic energy of the system. So what would actually happen is this block would go in the slow manner. Why won't it go in a slow manner? Because the acceleration of this block is not zero at all the points of its motion. Its acceleration would become zero at a single point, but at all points it would first accelerate and then it would deaccelerate to stop. So this is because of unbalanced forces are acting on the block. So what is the unbalanced force? Unbalanced force is the spring force, Kx. Kx is the spring force acting on this block, and this is the unbalanced force, and because of which the block is first accelerating and it is gaining some speed, it is gaining some kinetic energy. So one way to look that it would gain kinetic energy is by looking at the forces. We can normally say that friction won't be enough to stop force, so it would move. First of all it would move, it would accelerate. Next we would say since work is happening on the body, it would gain kinetic energy unless the work done is zero. And work done would be zero at what point? It would be zero at that point when change in kinetic energy becomes zero. That means work is not going to become zero up till the point the block stops moving. Up till then non-zero would happen on it, but the block would have some kinetic energy. So this is very useful in those cases where we have to find where the change in kinetic energy has to be equated to zero. That is the point. That when we have to find the point that, let's say, a block has started moving and it reached some point where it has stopped, then we say, okay, initial kinetic energy is equal to final. Then what is happening? Change in kinetic energy is 0. Change in kinetic energy is 0. That means the right hand side of the work energy theorem is 0. That means we have to look that problem from the side of work and equate all the work acting on the body to be 0, and its change in kinetic energy would automatically become 0. So this is again two ways of looking at the same thing. Unless there is non-zero work happening on the body, it would have having some kinetic energy by work energy theorem. And just when work done becomes 0, its kinetic energy disappears. So we would say work done by all forces is equal to some minus kx minus mu mgx minus half kx square and plus fx. So sum of all the work done should be 0. So this gives a very easy expression to look at. So we can say that this would be equal to some 2f divided by, let us do this properly and not by taking shortcuts. So we will say f is equal to kx by 2 plus mu mgx. So that means 2f by k plus 2 mu g is equal to x. So this is the maximum distance the block would go up till its motion ceases or it stops moving. So this is the question which we want to do. Let us do one more question. So the next question which we have is that of a mass m, where the spring is beneath that mass. So we have a mass m, it is kept in a pan. This is a pan in which the mass m is kept. It is balanced by a spring, so it is in equilibrium. It is not falling to the right or left, it is vertical. So it is not in equilibrium. In fact, that is the question. So this is the spring constant. Force is F. So some force is happening which is trying to balance the gravitational force and spring force acting on the mass. So initially the spring is relaxed. What we have to do? We have to find the work done by F up till the point the mass m is slowly brought from the natural length of the spring to the equilibrium length of the spring. And that is the question. So the key word of this question is slowly. What I said, that mass m has to be brought slowly from this particular point to its equilibrium point. So what would be the equilibrium point? Let us see first that equilibrium point would be when the gravitational force and spring force are balancing each other, and at that point F is not required. F is required at the point when spring force is not there. Then you have to bring the mass very slowly. So what is actually happening is, initially the mg is being balanced by a force F, which is itself mg. Now we reduce F by a very small amount. Now that small amount is taken by kx. Then again we reduce the F by a very small amount, and reducing F and the gaining of kx, it happens simultaneously throughout the motion. And at the point of the motion when mg is equal to kx, we have brought that at equilibrium. Right. Now this is a very interesting thing to study. What if F was not there and it was simply a system like this? So our question is that we have to bring the mass m at a point where mg is equal to kx. That means we know the final position. So we can write the expression work done by all forces is equal to change in kinetic energy, right? Since this is the work energy and theorem kind of question. So work done by F is some F is what we have to find. Then we have work done by gravity, work done by spring, that is minus half kx square, we can write directly. And sum of all forces that I told you in the last question. What will the sum of all the forces? I said that when the initial and final kinetic energy of the body are not only same but they are zero, since the system has to be finally brought at equilibrium and at rest, so the change in kinetic energy becomes zero. So from this we can write work done by F is simply half kx square, that is this term right here, and work done by gravity is positive, it would become negative, that would be minus mgx. So value of kx is equal to mg, so I can write mgx minus mgx, so that becomes mgx by 2. So this becomes with the negative sign, right? Since this is a negative, so this becomes x is equal to mg by k, so this becomes minus m square g square by 2. So with this we are done with the questions of work energy, and we learned in this class the idea of potential energy, and with the next class we will be doing some questions of potential energy and conservative forces. So thank you for joining and have a great day.